Alright, so here's a type of exercise that I honestly don't really enjoy because it doesn't really give you any insight into how you use the theorems or anything. It's just like, it's more a matter of like, oh, did you see this algebraic trick that you need to use? And then once you use the algebraic trick, everything is easy. Um, so when you're first looking at this sequence of n squared plus n, the square root of that thing minus n, you first might want to think, oh, are there any bounds that we can get? So just looking at it, we know that it's going to be greater than 0 because n squared plus the square root of n squared plus n. Well, if you remove the n part there, then you would just have, if you remove the n, then you would have the square root of n squared, which is just n. So this term is always greater than n minus n, which is 0. So it's always positive. And then in terms of like how large it could be, well, you could make that n inside the square root bigger by making it n squared. Particularly since we're sending n to infinity, so eventually it's going to be greater than 0. And so, or it's going to be greater than 1 eventually, and so replacing n with n squared will increase the term. So this term that we have is less than or equal to what would happen if you had the square root of n squared plus n squared. So that would just be the square root of 2 times n squared. So that'd be the square root of 2 times n. So this term is going to... I again have to write with the mouse because my stylus is broken, so I apologize for this horrible Khan Academy, very early Khan Academy awful writing. So this is going to be less than or equal to... so we'd have the square root of 2 times n minus n. So that's n times square root of 2 minus 1. Okay, so square root of 2 minus 1, that's just a positive number. And so we know that this thing can't grow faster than linearly with slope square root of 2 minus 1. But that's all we know. We know it has to be, it also needs to be greater than 0, but less than this term which grows linearly with n. But that doesn't really tell us about anything that the limit has to be. And so you might try thinking like, what could it be? And the answer ends up being 1/2, and there's no real easy way to see just by looking at the sequence that it ends up being 1/2. What you need to do is you need to do the algebraic trick, and the trick is you sort of do that thing from, I think, like pre-calculus or algebra 2 or one of those courses. I remember doing this in high school where you multiply by this thing, is it the conjugate? But anyways, if you've got a term with a square root and a term that doesn't have a square root, and you want to get rid of that square root, what you do is you multiply by that term with the square root, and then you also add the other term, but you change the sign. So you want to multiply it by that, but you have to multiply by 1, so you multiply by it and divide by it. And then when you multiply it out, the square roots completely go away in the numerator. And then you introduce the square root in the denominator, but hopefully things cancel out nicely. And they do. You get n squared plus n minus n squared in the numerator. And so that cancels out, and you just end up with n. And in the denominator, you've got this square root n squared plus n. Just that term there. Turns out you can factor out an n out of the square root sign because n is the same as n squared divided by n. So you're factoring an n squared out of the square root sign, and when it comes outside it becomes n. Then you just have 1 plus 1 over n. And so now we see that we have n's in every single term, and we can cancel them out. An important note is that we don't have to worry about n being 0 because we're taking the limit as n goes to infinity. So n will eventually be large enough that it's not going to be 0. So we don't have to worry about dividing by it. But then, so finally we end up with this thing 1 over, then we have square root of 1 plus 1 over n plus 1. And so here you're at a point where you can actually like use a theorem that we learned in the textbook. And the theorem is that if you're doing, if you're taking a limit of a quotient and the limit of the numerator and the denominator both exist and the limit of the denominator is non-zero, then the limit of the fraction is the same as the limit of the numerator over the limit of the denominator. And so the limit of the numerator, well, you're just taking the limit of 1, so it's going to be 1. If you look at the denominator, the 1 over n, that's going to go to 0, so you're just going to have, when you take the limit, you get the square root of 1 plus 1. So that's just 1 plus 1, which is 2. And so you end up with 1/2. So yeah, not a very illuminating exercise, not something that really teaches you to use the theorems from the textbook, other than that thing about taking limits and quotients. But it's really, I guess the only thing you can take from it is don't forget all of those like random algebraic techniques that you learn in like high school or maybe college, whenever you learned it. But it's like one of those things that like comes up in one of your courses and you're like, when am I ever going to use this? And this is a case where you actually use it. So you can't forget about those because one day they might be important for something. And of course it won't necessarily be something super illuminating, it's just you need to do some mathematical technique. But I mean, it works here and it allows us to compute an answer. So once you know the algebraic technique, you can evaluate the limit and you can get the answer, and then we're done.